So it's my great pleasure to introduce our speaker tonight, Horace He. Horace He graduated from Cornell in 2020, and he works at Meta on the PyTorch team, specifically at the intersection of compilers and machine learning. If you've used things like torch.compile, which is a thing in PyTorch that makes your model goes like 2 to 4x faster in just one line of code, or if you've used flex attention, which is something that lets researchers design fast kernel for attention without leaving the world of Python, is the person responsible for both of those things. You should also check his blog, which is pretty awesome, and in particular the blog post making deep learning go brew from first principles. And without further ado, I'll give it to Horace.
Thanks for the intro. Today I'm going to give a talk about building machine learning systems for a trillion floating point operations. My name is Horace He, and I'm on the PyTorch compilers team at Meta. So, I think we live in pretty unprecedented times in terms of infrastructure build-out, which is, I think, nicely reflected in NVIDIA's stock price. I feel like, basically every month we see like a different headline about like a new nuclear power plant from like Microsoft, or like a massive 300K GPU data cluster from XAI. People like I feel like when Amazon first like built like bought a nuclear power center, it was like a big news. But now practically like every cool AI company has their like own nuclear data center. And of course, this like kind of really massive infrastructure build-out has kind of also resulted in pretty ludicrous fundraisers from startups, I think. I remember back in like 2016, like if you like made it as a startup, it would be like if you were worth $1 billion, right? It's like a unicorn is like the mark of like really making it as a startup beyond your wildest dreams. But in 2024, you got to raise $1 billion just like get started. It's like just to play the game, you need like $1 billion. Of which most of it goes to NVIDIA. And so I think like it's kind of crazy to think that all of this like billions of dollars is really just to do like an absolutely insane amount of floating point operations. Here's like a nice chart from like Epoch AI showing like the growth of compute over time. And like these floating point operations are really just like big matmos done like over and over, for millions of iterations over like months. And nowadays, like the leading edge models are currently trained with about like 1e26 floating point operations, which is approximately 100 trillion floating point operations. So like a trillion teraflops worth of floating point operations. And so, back, another kind of effect that you might have noticed is like back prior to 2016, if you searched on like Hacker News, like ML, you'd often get like a lot of people asking about, the ML family of languages. But nowadays, you search ML on Hacker News and you get like a very different type of article. And so I think one of the things that kind of is missed here is like, with all of these like billions of dollars and like, yottaflops of operations, it's kind of easy to forget that like these operations needed to actually run somehow on the like machines. And so a modern stack might involve call like an LM API, and then this calls like PyTorch, like Nickel, Triton, CUDA, like MVCC, like all these like different layers in the stack that like somebody was involved in writing. And I'm often reminded of this like XKCD comic, showing like the state of like modern digital infrastructure. And so, you kind of, often have to forget about all the infrastructure that was involved for you to like get where you are. But like really, we're just kind of building like layers on top of layers. And so, if you work in systems, like I do, and it's like many of you do, you kind of, I think, oftentimes think about your work a little bit like a benevolent dictator of sorts, where kind of you imagine like what you're doing here is that like a lot of people build on top of your work. And so if you can kind of give like a small amount of improvement to like millions of people, your small improvements can lead to like significant impacts on the world. And so for example, I kind of imagine like Guido with Python, he just like kind of sits on top of his cloud and eventually like gives us like no-gil or like faster C Python or like the walrus operator. And I feel like this is kind of oftentimes like how I imagine like infrastructure work did, and it's kind of a lot of why I got into infra work in the first place. And so, on the other hand, I feel like if you work in ML, things can sometimes feel a little bit different. I recently came across this post on Threads where this person said, my main gripe with like working on top of like LM APIs is that you're not really like, no one is like engineering anything. You're just like chancing a prayer to this like man-made demon deity to like do your bidding. And this is like very similar to this kind of like Shoggoth metaphor that has become like very popular in deep learning circles. Where the idea here is that like we really like put all of these like mammals and like computation into producing this like very weird alien intelligence. And then we like kind of like RLHF it, and like provide it in this like nice, convenient interface to people with like ChatGPT or something like that. But I think if you think about it, I think we're kind of working with Shoggoths like all the way down. Even like if you're working like in systems and you're not calling like ML models, you still have this kind of like massive amount of infrastructure that you presumably don't really understand, written by people you probably never talked to, and like the end result, they try to expose as like some kind of a simple interface where you can just like import Torch and then hopefully run your code across like 100K GPUs. And so I think as a result, there are some, I think, interesting ways in which I think ML models feel kind of different from regular systems. One of those ways is that like ML models are extremely simple. And as a result, we have like very high expectations from the performance of like the code. I think you can kind of like trace all the way back to this very nice article called The Bitter Lesson, which I'd really recommend reading if you guys haven't come across it before. Where their main observation here was that like clever ideas in machine learning have basically throughout like its 50-year history always lost out to just simple ideas that like scaled really well with Moore's law. And I'm not really like joking here when I say that like machine learning logic is exceedingly simple. There's like this cool project from someone called like Andrej Karpathy called Llama 2.c, and basically here he's like implemented like Llama 2 in about like 973 lines of C with like no other dependencies. Like every single loop, every single like mammal is just implemented from scratch. So with 973 lines, you can't like do it very fast, but it does run, and I think it does kind of indicate just like how fundamentally simple the models that like we're spending all this compute end up being. And so the end result, like although like the problems themselves are extremely simple and like very like easy to optimize in some sense, the expectations are very high for how well we can optimize these mammals. So one example here is that like the predominant metric for measuring your like model's performance in deep learning is called model flop utilization. And so this is basically the like percentage of the theoretical max flops that your GPU is able to do. And so if you kind of think about this is actually like a very absurd metric to hit. Like if on a CPU, like you measured any of your code by this metric, like you can only hit 100% if like at every single time, every single core of your CPU is always issuing max width SIMD instructions. That's like the only way you can hit 100% utilization. And so if you take a look at any of the code that you guys presumably write, like almost no CPU code is like anywhere near like 100% flop. It's probably like way under like 1% most of the time. On the other hand, in like machine learning for like large scale training, we're typically often hitting around like 50% of like the peak flops. And this is, I think, like, this is kind of like indicative that like even though the overall problem is like very simple, the kind of corresponding difficulty just goes into like making your like models hit like this like very high perf barrier. Another kind of interesting observation in like machine learning is that has kind of exacerbated this a bit, is that the field has consolidated significantly over the last 5 to 10 years. So one of them is that like like maybe 10 years ago you had like a lot more architectures, a lot more variants, and like different things that people were trying. But nowadays people really just like transformers are like the dominant architecture for everything. Like you have transformers for vision, you have transformers for language, you have transformers for like audio. It's kind of like all transformers. And the other way like things have kind of changed is that instead of like many different people training SOTA models, you oftentimes just have a few companies training SOTA models. And so we've kind of gone from a bit of like a monopoly where like previously there was just like one person providing the infra and like many people using the infra, to in some ways it feels a little bit more like a monopsony where you have like many people trying to provide infra and then only one person is actually training the job at the end of the day. And so as a kind of result, I think that like there's kind of two general ways to think about like getting performance from like your systems. And so one of the ways generally is basically like optimizations. It's like you have a compiler, you like make the compiler faster, you improve like the performance of everybody using your compiler. And so the other way though is kind of like programming models. And so like this is kind of analogous as opposed to like a system whose responsibility is to like chop down a tree, and then you're just like optimizing how fast you can chop down the tree. And the other alternative is like you're providing tools for people to cut down the trees themselves. And so to kind of like talk a little bit about programming models, I think it's like illustrative to kind of talk about how like ML frameworks have kind of evolved in terms of what programming model they've exposed to users. So originally, like I think like 2010, like 2011, 2012, the first like ML framework that kind of got a lot of popularity was this framework called Caffe. And the way you like express neural networks in Caffe is like a very declarative nature, and by that I mean you like edited a protobuf file, I think, where like the protobuf like specified all the things you needed to care about your neural network. And so as you can imagine, programming protobufs is like not very fun. There's a lot of things you might want to do that you can't do in protobufs. And so a like natural net thing that people did was kind of these kind of graph builder type APIs. And so this is kind of how TensorFlow 1 kind of looked like, where the idea is that like programming protobufs, or like no human should need to write protobufs by hand. And so ideally, you should just like write like a DSL of sorts that allows you to generate the protobufs like from this DSL. However, like even this DSL still kind of has like a lot of confusion in it. Like it's not super clear that like given this DSL, like how code actually executes on your GPU. And so kind of finally, like around 2016 or 2017, PyTorch started to become like really successful. And kind of the feature that like was most emblematic of PyTorch was basically what was called imperative or eager execution. And so what this means is that like, so PyTorch was very successful, and I think it's like worth talking about like why eager execution was so successful. And I think that the main reason it was successful just comes down to like what the programming model of the execution looked like. Where in imperative / like eager execution, it's basically like you call a function, the GPU runs a function, and then the function finishes, and that's it. Like like that's basically all you do. You call like torch.matmul, and this is basically the sequence of operations that happens. But with kind of like a graph mode type approach, or where kind of this compiler interjects, you first like define the function gets converted into some like intermediate IR, a bunch of who knows what happens to your function, and then eventually like the function eventually executes on the GPU. And the top one was like a very simple execution model for people to understand. And I think another thing that's kind of interesting to notice about this is that this kind of also just like the top half also kind of describes how Python executes. And I think this is kind of pretty illustrative to me of like why Python has been so successful in machine learning. It's basically that like a funny statement that you can make about Python is that like if you tried to like train a model today, like I gave you like a day to like train a model, it would run faster if you ran it in Python compared to doing it in C++. And you might argue that this is like a unfair comparison because all the infra, all the frameworks that people build are in Python. But I think the reason why so many of these frameworks have been built in Python is that Python is like an exceedingly like a simple language, and so it's also like a very growable language. And what I mean by like growable is that like it's very easy for people to build their own infrastructure on top of Python without really needing to fight with like anything the Python language does. Because the Python language itself does basically nothing. It doesn't do any optimizations for you. It just takes your function and runs it. And so I think that PyTorch basically historically is at like a very similar point in the design space, where PyTorch is like execution model is like so very simple. And although this like doesn't really give you a lot in terms of like it doesn't like automatically do a lot of things for you, it does mean that it's very easy for people to like build their own infrastructure and frameworks on top of PyTorch. I think another important detail to realize, especially about like PyTorch when it first came out, is that like this kind of unoptimized execution didn't actually even sacrifice any performance at all. Like, when people kind of benchmarked PyTorch versus like, TensorFlow or Caffe, PyTorch oftentimes wasn't even slower than those frameworks. And I think there's like two main reasons for this. So the first reason is that back in the day, like, about like 90% plus of your time was spent in matmals. And so there's basically like nothing else you need to optimize. And so matmals here are like matrix multiplications. And so they're often provided by these like vendor libraries like cuBLAS or like cuDNN. But like, they're provided by NVIDIA and they're like very hand optimized. And so, if 90% of your time is spent in matmals, then like what else can you even do to like optimize the performance of your neural network? And I think another kind of interesting important piece here for like why PyTorch's performance was like quite good is that it had this like async execution model, where basically the idea here is that like you kind of have like a parallel work queue on your GPU. And so what the CPU does is that it's only responsible for scheduling work on your work queue, and then the GPU executes work from the work queue. And I think of it generally as like this GIF is what usually comes to mind. And basically, you can imagine that like the dog is like, or grommet is like Python. They're like trying to put down the train track in front of the train, which is the GPU. And so as long as like grommet is able to put down the train tracks faster than the train actually rolls along the train tracks, you can actually kind of view Python as like having zero overhead. Like it doesn't provide any extra cost compared to if Python was like in a more efficient language like C++. And so in this way, like eager execution not only had like a much easier to understand programming model for users, it was also like basically just as fast as like non-eager execution. Unfortunately, good things never last. And in 2017, like NVIDIA introduced what are called like tensor cores. And if you guys are unfamiliar with tensor cores, they're basically like hardware units on the GPUs that only do matrix multiplications. Like, and I don't mean this like figuratively in the sense that like people often say that GPUs are like well suited for matmals. I mean this like very literally in that like there's actually an assembly instruction that just does like a mini matmal, and this is how you like interact with the tensor cores. And so if you look at this like plot of like the amount of like matmal flops versus non-matmal flops, you can really see like when NVIDIA realized that like deep learning was a big deal. Because like all of a sudden, you kind of had this like massive like 10x gap, and so this is like a log scale, and you had this kind of like massive like 10x gap between how fast matmals were on the GPU and how fast like literally anything else you wanted to run on the GPU was. And so the end result is previously we said that like matmals took like 90% of the time, and so if like NVIDIA sped up matmals by like 10x, but then everything else like stays the same amount of speed, then all of a sudden, like you need to spend, you're spending a lot more of your time doing like non-matmal operations. And so as a result, we've kind of gotten like ML compilers due to this, I think largely due to this change. And so one of the, I think the important details about ML compilers, like, in terms of like how they differ from the frameworks that came before, is that ML frameworks still keep like the eager programming model, in that like the code that you write, like logically the programming model exposed to users is that you're still just writing Python code and it executes like line by line. The only difference now is that instead of actually executing line by line, we kind of captured it into like a graph in some manner. And so Torch compile, I think, actually kind of does this in a pretty interesting way. And that Torch compile actually like intercepts at like the Python bytecode interpreter level, where Python kind of exposes these APIs where you can kind of insert your like own frame interpreter. And so this looks very much just like a traditional like JIT for like any kind of other VM, except this JIT is kind of only meant for like PyTorch programs. And so if you kind of look at like how like things have evolved over time, originally you kind of had like frameworks like TensorFlow or Caffe before that, where both the user like programming model that users wrote was like a graph builder type abstraction. But then the execution programming model was also a graph execution type abstraction. And then like after that, you kind of had PyTorch 1 type like stuff, where the user programming model now switched to like an eager style execution, but the execution program model was also eager, where like each operator is executed one at a time. But kind of now finally modern ML frameworks, like pretty much all ML frameworks nowadays, use like an imperative eager programming model. But almost all ML frameworks now also have some way to like capture this program model into a graph of some kind so they can perform optimizations. And so this is like, Jax.jit, this is like tinygrad, this is like MLX. They kind of all have their like different approaches for capturing the graph to optimize. And so I think next I kind of want to talk about, we've kind of discussed how we've gotten to ML compilers in the first place. And so I think next I want to talk about like what ML compilers are actually doing for you and what kind of optimizations they're performing. And so generally speaking, the way I think about deep learning performance or like performance on GPUs in general is that there's basically three things you can be spending your time on. The first one is compute. So this is time on your GPU computing like actual floating point operations. The next one is memory, which is time spent transferring your tensors within a GPU. So this is like across various memory subsystems in your GPU. And so finally, like overhead, which is like everything else, like it's like time your GPU is spending idle and so on. And so first, we're going to talk about compute. And so I think to a sum approximation, you can say that all runtime on your GPU is either compute or it's shuffling data. And that like data movement is like not like a real operation, right? It's like a no op from like the theoretical point of view. All it's doing is it's moving data from one place where it's convenient to another place where it's convenient. And so basically, a floating point operation is like the only real thing a GPU can do. But you can actually, I think, simplify this even more and say that in reality, actually nowadays, like all runtime is either like matmuls or essentially shuffling data. And so this is like because if you look at the actual like flop chart on like an H100 like GPU, you can see here that like the FP32 flops is like you only have 67 teraflops of FP32 compute, but you actually have like 1,000 teraflops of TF32 compute, which is basically like matrix multiplication compute. And so what this essentially, in some sense, like what this means is that if you're not doing matrix multiplications on your GPU, you're really only like getting like 7% of like your peak flop utilization. And so by like the metric that I mentioned before, like model flop utilization, even if your GPU was fully occupied doing stuff that wasn't a matmul, you could only ever get like 7% flop utilization, which is like much lower than our theoretical peak. I did have a brief interlude about like I think an interesting case where like these kind of abstractions do break down even more. And so I do have like a kind of a fun question, which is like, do the matrix contents affect your matrix multiplication performance? And so I think if you kind of are familiar with like general performance, there are like a lot of ways where like data can impact your performance. But in this case, matmuls actually avoid a lot of them. So for example, they have identical memory access patterns regardless of like what data is in your tensor. There's like no control flow in the matmul, and the GPUs also don't have like denormals. So like that's like not a possibility as well. So if you like, and in this case, we're like taking 3 tensors, we're initializing them with like all zeros, like a tensor initialized from the Gaussian distribution, and then a tensor initialized from like the uniform distribution, which is like from 0 to 1. And so funnily enough, if you benchmark this, you actually find that there is a performance difference depending on the actual data that is within your tensors. And so there's this tweet from somebody you guys might know a long time ago that really, I think, like when I first saw this, I actually was very much reminded of this tweet where I thought I knew how like a GPU worked, but then I was like very confused about what could possibly be causing these like performance differences, like between the different data. And so the actual cause here is something called like leakage power or dynamic power, where I think most of you are probably familiar that when a CPU or GPU is under load, it uses more like power, and at some point it can like throttle. It's like using the max amount of power it can use, or the max amount of like heat it's allowed. But the actual thing is that like this power doesn't just like come from nowhere. It actually largely comes from what's called like dynamic or switching power. And what this means is like every time a transistor like on the GPU switches from like 0 to 1 or like high to low or low to high, it like loses a little bit of this power. And so the actual like power usage on your GPU is kind of like a like sum across the total amount of like switching that goes on in your GPU. And so this is why, like, if you're multiplying with all zeros, you can imagine that like your GPU ends up not, like a lot of transistors don't end up switching at all. And so like it doesn't actually consume that much power, and it's much less throttled. And so if you actually like look at this, you can actually get like very different performance for like all these different kind of fun distributions, like whether it's like the normal distribution, or whether it's like a checkerboard type like pattern, or it's like sparse or ternary. And the reason why is just like it's like this kind of abstract thing where these different patterns lead to like more or less transistor flips, and which leads to like more or less power throttling, which leads to like more or less performance. And so I remember actually one time somebody told me a funny story where like they were like training their machine learning model and benchmarking performance, and then they like at some point their model would nan, and then they'd be like, "Wow, my performance just got way better." and like so I like wrote an article about this, and they like messaged me, and they were like, "Oh, that was very illustrative," because I was really confused why my performance would be getting better. But that's why, like if all your tensors are nan, your transistors also don't need to do a lot of flipping, and so you'll measure like a better perf. So that's kind of compute. And so the next thing that your GPU can be spending a lot of your time on is like memory, which is essentially time spent transferring your tensors within a GPU. And so I think one thing to observe from this kind of empirical plot from a paper on like data movement is that although like so this paper kind of breaks down the operations on like I think a BERT type model into what it calls like tensor contractions, i.e. matrix locations, and then like normalization operations and element-wise operations. And so you can see that although matrix locations are responsible for like 99.8% of your flops, they're only responsible for 61% of your runtime. And so why are we spending like 40% of our runtime doing like operations that cumulatively only take 0.2% of our flops? The kind of key thing here is what's called like memory bandwidth cost, where the way I typically think about this is that like even like and so here I'm talking like all of your data already lives on the GPU. Like it's like occupying your like GPU's VRAM. But the thing is that like your GPU's VRAM is not where like the compute units are located, and in order to actually do operations on a GPU, you need to move your data from like the VRAM to like where the compute units are located, which is like your SRAM or like compute units. And so usually I kind of think this of like as like a factory, where you have like a factory with like not that much space, and then you have a warehouse located like much further away. And so you have like a lot more space in your warehouse, but now in order to do any operations like on those supplies, you need to move them from your warehouse to your factory and then back. And so this cost of like moving data around is called the memory bandwidth cost. And so this is actually like responsible for like a lot of like what your GPU is spending its time doing. Where if you imagine like let's say we do like 3 operations like on a GPU, so maybe you're doing like an add and then like a ReLU and then like a sign operation. Like you can imagine that what actually happens when you do these operations is like first the GPU sends the data from like the memory to the compute units, and then turns it from a square to a triangle, and then it sends it all the way back, and then it sends the triangle from like the memory units to the compute units again, where it does like another operation and then sends it all the way back, and then finally you guys get the idea. It's like sending the circle from the memory units to the compute units again, and then it's like sending it all the way back. And so by default, whenever you run any operations like in PyTorch, like let's say you ran like add and then multiply and then cosine, this is exactly what would be happening on your GPU. And so you might think that this is a very like dumb thing to do, and you would be correct. And that why are we like sending our triangle back from like the factory to the warehouse just to send the data from like the warehouse back to the factory again? And so a very like common operation for GPU compilers to do, and I'd say what I would actually call like the most important optimization in a deep learning compiler by far is called operator fusion. And so what an operator fusion does is that instead of like sending the data back and forth so much, we like do a single GPU kernel where you send the data once to the factory units, you do all of the operations, and then you send the data back. Also notably, this is also like an issue. This optimization is not really something you can do in eager mode, right? Because in eager mode, I was mentioning like the executor model is very simple, where you like run an operation and then it executes the operation. And now, if we want to do this optimization, that programming model is like no longer sufficient. And so there's actually like a lot of different ways to minimize memory movement. Although at the end of the day, like operator fusion is like the most important thing you can do for like an ML compiler. There's actually like a lot of decisions that go into operator fusion that like kind of enable it to be more or less effective. One of the kind of examples here is kind of these like recomputation versus reuse trade-offs. If you guys are kind of familiar with maybe like register allocation type settings, you kind of often have a similar issue where like if you have a register, you can choose to either like store it in global memory and then load from it later, or you can just choose to like recompute that value from like values that are already in the registers. And so you kind of have a similar idea here, where you oftentimes have cases where by doing some amount of recomputation, you can significantly reduce your memory. You can significantly reduce your number of memory accesses. And so in this way, like the recomputation can not only like reduce your like peak memory usage, it can also often like improve your actual runtime performance. And so I think one of the things to mention actually about like why, so this optimization actually ends up being like quite important for deep learning performance, like recomputation versus reuse. And I think the reason why is that like the shape of machine learning programs actually I think looks quite unusual compared to like your typical program that you might have, where like it's generally like a kind of a bit of an axiom in like programs that usually most intermediates that you have are very short-lived. So like your program generally consists of a lot of very short-lived intermediates that are created and then very shortly destroyed. But in machine learning, this is actually not the case, because in machine learning, like the typical like model that you'll execute will first like run the model forwards, like layer 0 to layer 1 to layer 2 to layer 3 to layer 4, and then it needs to run what's called the backwards pass, which will like run the layers in reverse. So then it will go from like layer 4 to layer 3 to layer 2 to layer 1 and to layer 0. And in between the forwards pass and the backwards pass, you need to save what are called like intermediates or activations. And so these are like a lot of like, you have a lot of them. And they're like oftentimes like largely responsible for like running into like out of memory type errors. And so I think this is actually like kind of a pretty unusual like program structure in machine learning that's caused by like backpropagation and gradient descent. And so finally, the last thing you can be spending your time on is overhead, where you can imagine that if poor grommet is not able to put down the train tracks faster than the train can like go on the train tracks, then sometimes the train is going to be just stuck waiting for him to put down like the next train track. And so here I have like a profile trace where you can see that like the bottom line, which is a GPU trace, is largely idle, and it's mostly just idle waiting for the CPU to like schedule the next operation. And so there are a lot of like ways to actually address this nowadays. One of the most powerful is called CUDA graphs, which is like an NVIDIA-provided API. But you can also have like other approaches, like in a compiler, for example, like code-genning like a lower overhead wrapper or something like this. So I've talked about like ML compilers, like, and what they can do to your program and how they can be useful. But I think kind of like an interesting question that you often see, like I talked a lot about how like we have like super massive infra build out, and the programs are super simple, and we've seen like a lot of consolidation in terms of like what the architecture looks like. And so I think like a reasonable question is like, if you only have like one architecture and you're spending like billions of dollars to train it, why do you even need a compiler? Like why can't you just like assign some group of people to like optimize it by hand instead of like leveraging a compiler? I'm going to say some like kind of, and the other thing I'll say about this actually is that like in practice, a lot of times people do not use compilers like for kind of this reason. And so this section is going to be talking a little bit about like why I think that's the case and what are kind of some of the challenges when it comes to like using compilers in this setting. And yeah, so disclaimer, I do really like compilers. I'm going to say some kind of mean things about compilers in a bit. But as like to establish my credibility, I work on a team called PyTorch compilers, and so there are to be clear, a lot of reasons why compilers can be very useful. In particular, this kind of notion of leverage, like being able to do the optimization once in the compiler, and then having everybody be able to take advantage of it. And then also, compilers are also just very fun to work on. That being said, yeah, I'm going to introduce you, my new exciting library, Horace's exciting library, abbreviated HEL. And so it has a couple of cool features that you might be interested in. So the first feature it has is that it doesn't always work. And to address that, it also has no documentation about why or when it will work, except by reading my library's implementation. And in exchange for that, when you update the library, it may totally change what code works and what code doesn't work, i.e. no backwards compatibility or guarantees on your on whether your code works. And so, are you interested in using my library? I guess most people would probably say no. And so I think one thing to note here that if work means has a desired performance and is applying the desired optimizations, this is kind of largely describing how compiler optimizations work. And that compiler optimizations don't always work. They are often there's no real documentation on when a compiler optimization will trigger. And when you update your compiler, it may completely change when it does or does not apply these optimizations. And so there's very influential to me article called about this compiler called ISPC, and they have this note here called auto-vectorization is not a programming model. Where they note here is that the problem with an auto-vectorizer, which is kind of a compiler, or so the overall framing of the article is that he wrote this compiler called ISPC, which you can think of as CUDA for Intel SIMD instructions. And he kind of is constantly as part of the article is constantly trying to fight against the Intel compiler team, which is where he worked, where the Intel compiler team wanted to kind of leverage auto-vectorization to get vectorization done instead of introducing a new programming model in ISPC. And so he kind of, I think, elucidates what the problem with the auto-vectorizer, which is that the problem with the auto-vectorizer is that as long as vectorization can fail, and it will, then if you're a programmer that actually cares about what code the compiler generates from your program, you need to deeply understand the compiler, you need to deeply understand the auto-vectorizer. Then when it fails to vectorize code, you want to be vectorized, you need to either poke it in the right way or change your program in the right way so that it works for you again. And so this is a very horrible way to program. And then, if most of you, or if any of you here are very into using SIMD instructions, you probably also do not trust the auto-vectorizer at all, and you're mostly just writing intrinsics. And so with a proper programming model, ideally, the user is able to learn what does and does not work without needing to be tied to the implementation. And then one compiler implements it, and then the user can learn to reliably rely on this optimization without needing to understand the compiler and only needing to understand the programming model. And so one, I guess, way you can phrase this is that a compiler optimization that always works is just part of the programming model. For example, when you're writing SIMD instructions, you know that a SIMD instruction will, a SIMD intrinsic will always get mapped to a SIMD instruction. And so that's part of your programming model and not really an optimization that the compiler is doing. So I think when I see the people kind of complaining about Shoggoth and working with them, I kind of am often reminded times of a compiler. We can imagine that a compiler is oftentimes this large piece of code that has been worked on by a lot of very smart people and oftentimes has a lot of tricky details and implementation details in it. And so ideally when you're doing a compiler, only the programming model ends up being exposed to the user. So the actual compiler implementation ends up being completely hidden. And so the user only needs to deal with the nice programming model, which is usually just the language that the compiler is compiling from. Unfortunately, when compilers fail and they don't apply the optimization that you want them to apply, the kind of entire thing becomes exposed. And so this kind of applies any time that you're struggling with it, you're wrestling with a compiler and you're trying to understand why the compiler did or did not inline my code or things like this. And so to give some examples of cases where very kind of nuanced details here can lead to compilers struggling a lot. One of them here is like numerics and machine learning, where numerics can be like a kind of like in general, floating point like arithmetic is like a very cursed thing to deal with, generally speaking, and it's just gotten even worse with the fact that like NVIDIA, and not just NVIDIA, like everybody in the industry keeps on pushing our data types lower and lower bits. Where like on the V100 they kind of introduced like 16-bit operations as kind of the default, and on A100 they introduced 8-bit operations. And on the B100, they're now pushing for like 4-bit like 4-bit floats and operations on 4-bit floating point numbers. I think it's reasonable to question like how is this even a floating point number at this point? But this is kind of what we're typically dealing with. And so as a result of like this kind of like low precision and the fact that numerics end up being so subtle, you oftentimes have like very annoying numerical problems to deal with. And I think a good example for me that was like very frustrating was this kind of a NAN in like a flash attention implementation, where the underlying cause here is something called an FMA, or like a fuse multiply accumulate. It can actually be like disastrously bad when it comes to your numerics. So for folks who are unfamiliar with the FMA, it's basically like it takes like A, B, and C, and it does like a single operation that does A times B plus C. And so one of the ways that FMA differs from normal operations is that in addition to being faster, it's also usually computed in what people call like infinite precision internally. And what that means is that like the result of your FMA is like the closest possible representation to like the true value of your FMA. And so this is different from like if you just did this operation separately, where typically after your like multiply operation, you would have like a rounding term where it becomes a bit different. And so in this particular case, we're computing exponent of like AI times B minus a maximum scale, where max scale is like a singular scalar value that's a result of taking the maximum across AI times B. And so the main idea here is that exponent is like a very numerically unstable operation, and so we want to make sure that like we're not taking any very large exponents, and so we're subtracting out the maximum value so that all the exponents, like the maximum size exponent that you can get here is 0. And the compiler in its wisdom helpfully rewrites this as like FMA of AI B negative max scale, where it's smart here. It actually realizes that it can rewrite the plus into like a plus and minus. But then if you actually look at the numerics that are going on here, max scale is like a rounding of AI times B, and we actually end up computing this quantity instead of like exponent of AI times B minus the rounded value of AI times B, which can be disastrously off. And so the end result here is that we NAND with FMAs turned on, and you don't NAND with FMAs turned off, even though FMAs are like theoretically a precision improving optimization. The underlying cause here, to summarize, is basically that our numerical properties relied on 2 separate computations of the same value to be exactly identical. And in this case, with FMAs, you can apply them to only one branch, but not the other branch, and this leads to like NANDs in this case. Another thing that compilers oftentimes struggle with are what are called algebraic rewrites. So if you guys are familiar with this optimization called flash attention, which kind of like fuses attention operators together, it actually relies on this like kind of subtle rewrite, which people oftentimes call like online softmax, which is that typically softmax is implemented with a couple of like global synchronizers, I suppose. But you can actually rewrite softmax in a way that removes one of those global synchronizations. But this requires like some amount of math. It's not very hard math, but like compilers are generally very bad at math, and so it's kind of difficult for them to actually come up with this rewrite by themselves. And so I think flash attention is like a very good example of like a case where you need to think about the programming model you expose for flash attention. Where before this like fused attention kernel came about, people just typically wrote attention like this. You did like one matmul, and then you did a softmax, and then you did another matmul. And this was like not super efficient, but it was as efficient as you could do, so people were happy with it. But unfortunately, with flash attention, we now want to fuse like these 3 operations into a single kernel. And so like the difficulty is like, what API do we expose for flash detention? And so one way you might like tackle this is a pattern matching. So you can use a compiler, try to find the sequence of matmul, softmax, and matmul, and then pattern match it into a single flash detention operator. And so this is like a reasonable option, but the issue here is that it becomes very frustrating to debug. Like for example, the user might change how they write softmax. Like they might re-implement softmax with their own softmax implementation instead of using your vendor-provided softmax implementation. And then all of a sudden your pattern no longer applies, and they're sad because the memory suddenly blows up and their code is 3x slower. And so this is very frustrating for users to deal with. And so instead, what PyTorch did in this case is that we just said, okay, these three operators now need to be fused into one operator. We're just going to directly provide you that single operator as a single API that you can call. And so this is one way typically they can deal with programming models, is you can just kind of introduce a slightly higher level thing that does a very specific thing for the users. But this is also still kind of frustrating. And you might have some questions about whether this is actually good enough to do, because when you consolidate multiple more primitive APIs into a single more monolithic API, you oftentimes run into issues where the monolithic API is now no longer able to represent all the things that users want to do. And so with attention, we do see that people kept on coming out with new attention variants, sliding window attention, alibi, page attention, neighborhood attention, all this kind of stuff. You look on Twitter and a new 4 attention papers come out every single week. And as a result, the kind of fused attention kernels that people have keep on accumulating new quarks. Flash attention, this one's from the flash attention repo. It now has a dropout, a softmax scale, a causal one, a window size, a soft cap, alibi slopes, and so on. And some of these were added in the past couple months. And they just keep on adding them. And once you've added a quark to an API or to a programming model, you can't remove the quark anymore because now that's breaking what users rely upon. And even worse, even though people have been kind of aggressive about adding new quarks, it still doesn't end up being enough. And you have all sorts of users who are constantly complaining that nobody has implemented flash attention for their pet attention variant. There's no flash attention for prefix LM. This bottom one was from a blog post from somebody who used to be at Google who was complaining about the ecosystem outside of Google. And so basically the point here is that a single monolithic operator is not actually always sufficient. And so we're in a situation where compilers, we don't really want to rely on a compiler to generate from scratch, but it's also painful to do modifications by hand. And so this might kind of seem like a no-win situation where you kind of must choose one of them. You must choose either unpredictability and doing it as a compiler optimization, or you must choose a single monolithic API that's difficult for users to modify. But this is kind of where you kind of can be clever and come up with a new programming model that wasn't either of the programming models that users had before. So one thing to notice here is that this kind of custom kernel that's difficult for a compiler to generate from scratch can actually be decomposed into a handwritten / complicated flash attention kernel, and a bunch of trivial modifications from users. They can actually be very mechanically generated. And so here we have an API that we've introduced recently called Flex Attention. And I really like Flex Attention, and I think we've seen very positive reception from the community, including from I think users who traditionally don't actually use compilers that much. And so one of the reasons that Flex Attention is so liked, even though it relies on Torch compile to work, is that it's guaranteed to always result in a single fused attention kernel, and it's always guaranteed to have the same memory properties as a fused attention kernel. And so this means that the user now has a programming model that they can rely upon, where they can kind of program against this programming model and try a bunch of different variants that all fit within this programming model. And the user does not need to understand how the actual API is implemented under the hood. So to give you guys a bit of a peek at how this API looks like, if you guys are familiar with like sliding window attention or causal attention, here you can kind of implement causal attention by checking whether like your query position is like greater than or equal to your KV position, and then also checking whether the distance between them is like less than your sliding window size. And then you can just like AND these masks together to get your like sliding window causal attention. And so the way we kind of think about, and so this is, I think, a good example of where compilers can provide a lot of value for users, even in these like super like handcrafted scenarios, where like previously, prior to this API, this attention API, you kind of have this situation where you had a bunch of these like, you had this like big cube of like, like masking or like positional biases, or whether it supported training or whether it supported inference. And a bunch of these dots were like filled in with users who had manually implemented attention kernels. But now with flex attention, every single one of these like dots are like now filled in. And so it's now like consistently users can rely upon fused attention kernels regardless of like the attention variant that they're using. And to give an example of like some stuff that users have been doing with flex attention, you have on the left like a bit of a fun attention mask from like some guy on Twitter, where basically in this case he had like a bunch of like molecular graphs of like different sizes, and he was able to convert this into like an attention mask that flex attention supported. And so this is like a very weird mask that I definitely did not think about when developing flex attention. But when you've developed like I think a good programming model for users, users are oftentimes able to do things that like you never considered doing when you developed the abstraction. Another kind of analogy that I sometimes think about when it comes to like optimizations versus programming models is there's kind of like a famous I think quote from Grothendieck about like tackling math problems, where he said that when you tackle like a math problem, you imagine a math problem as like a walnut, and it's like when you're trying to open the walnut, you can either tackle it by like just hitting the walnut a bunch and like opening it up, or you can kind of like soak the walnut in water and kind of establish like new like mental models for how to think about the problem until eventually like the walnut just opens by itself after being soaked in water. And so I think about programming models like very similarly, where like if you think about like auto-vectorization from like the Intel compiler folks' perspective, he had this kind of fun anecdote where like he said that the Intel people kept on asking like what happens when the CUDA compiler fails to vectorize, and he was like absolutely baffled about what happens. Like he felt like this was just a thing he needed to understand to like understand how the Intel people needed to change their compiler to be more competitive. But the kind of like misunderstanding here is that like it's almost a nonsensical question to even ask like when does a CUDA compiler fail to like make your code parallel? Because if you've written your code in CUDA and in the CUDA programming model, it like must be parallel. Like it's kind of like an axiomatic part of the programming model. Like there is no way you can write a CUDA program that does not execute across multiple cores. Like you can write CUDA programs that are like incorrect or deadlock, but they're still guaranteed to always run across multiple cores. And this is because the parallelism is inherent to the programming model in CUDA, while the parallelism is not inherent to the programming model of auto-vectorization. I think I think kind of ML compilers and kind of how they apply to like just generally optimizing GPUs, I think like is already quite difficult. But you have a lot more issues when it comes to like making GPUs run at scale. And so when you come to like getting GPUs to run at scale, I do think there are a couple of like kind of interesting differences between distributed ML programs versus like traditional distributed systems. And so one of the differences is that traditional distributed systems oftentimes are just trying to scale a QPS. And so when you're like trying to scale QPS, you have a lot of like very small interchangeable queries. And like the performance per hardware is like not like that critical. And then oftentimes you're willing to like double your amount of hardware used in order to get like fault tolerance or like like higher uptime or things like this. On the other hand, in ML systems, we just basically have like a single query. Like you're just like training your ML job. We have frequent global synchronizations across all of our hardware, and performance is like extremely important. So much so that like there's no way we could tolerate like a 2x loss in performance for basically any reason. And so one way to kind of think about how you can parallelize programs, and this is actually like not specific to ML, this is kind of a general like a way to think about parallelizing programs, is that you can think that there's basically you have like this cube of computation to do, where one of the dimensions is like the batch dimension, so it's like different tasks that you can perform. You also have like the within task dimension, so like the different operations within a single task, and then finally you have like the time dimension, which is what your GPU is doing at any given point in time. And so you can think of data parallelism as basically just splitting along like the batch dimension. You can think about like task parallelism as splitting across the task dimension. And then you can think about pipeline parallelism as kind of like splitting across the time dimension. Yeah. And so for data parallelism, the basic idea I think is like pretty simple, which is just that we have like a bunch of different tasks. We have a bunch of parallelism. And so each GPU just handles a different task. And so because of that, we just put one task on each GPU and then run it. And this seems like very nice and very trivial. But the issue is that like we have a massive synchronization of parameters after every step. Because after every step that we do, like the gradients need to be like synchronized across all of your hardware. And you can't just avoid synchronizing your parameters because you also have this kind of like mathy constraint from like the ML training side, which is that you simply can't train with like too large of a batch size, or your model just will not converge properly. There's also kind of another detail here where like you can't just like naively replicate your parameters. People oftentimes use like what's called a fully sharded data parallel. The second kind of parallelism that you have is like task parallelism, which is commonly known as tensor parallelism. And in this case, you basically just have two GPUs that split the same task. And so the main problem that you run into here that's kind of specific to ML is that like task parallelism, because you're like running the same task, does not oftentimes have like obvious ways to overlap your communication with your computation. But nevertheless, because the performance is so important, we still really want to overlap the communication. And so there ends up being like a lot of kind of involved things that people do to try to improve the overlap. One of them here is called like async tensor parallelism, where the general idea here is that you have like a communication op followed by like a computation operation. And so usually, while you're doing the communication, the GPU can't do any computation, and so this is like wasted idle time on your GPU. But the observation here about async tensor parallelism is you can actually kind of like mini pipeline your like communication and your matmul, where even within like a single tensor operation, there's still oftentimes like a batch dimension that you can parallelize along. And so by like doing this kind of like micro pipelining of your like communication and computation, you can actually still enable overlap even though like we're doing tensor parallelism. Finally, the kind of last kind of parallelism that we have is a pipeline parallelism, where the general idea here is that you assign like the first part of the task to the first GPU and the second part of the task to the second GPU. This kind of differs from tensor parallelism or like task parallelism in that in this case, you do not run on the same task with both GPUs at the same time. And so in this way, you can think of the task as actually being sharded across like the time dimension. And so there are a couple like additional wrinkles here about pipeline parallelism that are kind of unique to ML, I think. So one of them is that once again, the frequent massive synchronizations prevent us from like filling up the pipeline. But the second issue is that like back propagation, like the forwards and backwards pattern that I mentioned before, also adds like a lot of very fun wrinkles to your pipeline parallelism schedule. And that in this case, this is kind of like a pipeline like that people have designed, where the blue boxes are like the forwards pass, the cyan boxes are like the backwards pass, and then the green boxes are like the backwards pass split up even more. And in this case, like the main kind of nuance here is that you can see like there's various points here where your pipeline can actually choose to either run a forwards microbatch or like a backwards microbatch. And so this kind of like choice is not something you need to deal with in like a traditional pipeline parallelism setting, and it ends up leading to like a lot of different like optimizations that people do with pipeline parallelism. And so kind of like putting this all together, this is a diagram from the Llama 3 paper where they showed like what's kind of being done to train Llama 3. And so in this case, you can see that we're combining like tensor parallelism, i.e. task parallelism, with data parallelism with pipeline parallelism. And there's also a fourth one thrown in here called context parallelism. But you can think of that as just like another form of task or tensor parallelism. Yeah. And so I think, again here, like compilers, I think, have historically struggled quite a bit when it comes to keeping up with the distributed optimizations that people do. And the main reason is that like compilers are dumb and humans are smart. And what I mean by this is that for any given set of parallelism schemes, or like any given set of parallelism configs, it often is pretty feasible to create like a automatic model for the compiler to determine how to automatically like parallelize your program. But the issue here is that actually that like most of the innovation in parallelism doesn't come from like searching within your existing search space. It usually comes from like expanding your search space along a new dimension. And so this is something that compilers are not like super great at. And it's been one of the struggles when people kind of try to like automate parallelism with compilers or like general systems. And yeah. For example, like one of the additional like kind of wrinkles that have kind of shown up at certain scales is a fault tolerance, where when you're running like on like 10 or 20,000 GPUs, like where we're doing these like globally full synchronizations across all of our GPUs, we have this issue where our GPUs can fail for like all sorts of reasons. Some of them might be like user related, some of them might be like hardware related, some of them might be networking related. But basically, like a single failure takes down your entire run, and this is like quite problematic. And so this table is from like a paper that Meta published about like training Llama 3 and fault tolerance. And I think like one kind of example of like how this ends up being like an interesting issue is that when you're training on like 16,000 GPU hours, you're only getting like a error once every 1.8 hours. But now if you like scale it up to 131,000 GPUs, you now get a failure like every like 15 minutes or so. And so like this turns something that might not be that problematic at 16,000 scale or smaller into something that's like very problematic at a 131,000 GPU scale or even higher, where you can imagine that now you have a situation where you might not be able to make even a single step before a single GPU in your entire fleet fails. So to kind of conclude, I think ML has basically become the single most important computational workload in the world over the last decade. Maybe a bit biased, but I think by like the amount of like flops and investment, I think you can make a strong case for it. But the kind of characteristics I think of the workload, both from a social POV, like the massive infrastructure required, as well as a technical POV, I think kind of often does mean that a lot of the traditional approaches to building systems or compilers don't directly apply. Like you can't just like build a compiler and then have people who just optimize a compiler for like 5 years without thinking about how the workloads are evolving on top of them affect their compiler. And so I think to me like the kind of most interesting question about building systems here isn't really about like building the right optimizations for systems. It's instead about like coming up with the right programming models for expressing like your systems, and kind of coming up with the right programming models to enable people to kind of like do their own optimizations and kind of like build the next 100,000 GPU model. Thanks for coming to my talk. Hope you guys liked it.